Hello maths fans, Dr. Tom Crawford here from the University of Oxford, explaining how to use the method of the discriminant to classify critical points for a function of two variables. Last time we saw how to find the location of the critical points by solving for the partial x and partial y derivatives both equal to 0. Now for this particular function, f of xy is x squared plus 2xy minus y squared plus y cubed. We went through this calculation and we found that our critical points were located at 0, 0 and at minus 4/3 and 4/3. And now what we want to do is to be able to classify what type of critical point we have at each of these locations. For a function of two variables, there are three different types of critical point that we can see. So we have a maximum, and if you plot z equals minus x squared minus y squared, if you enter this equation into your Maple calculator app, it will show something that looks like a large hill, and the point at the top 0, 0 will be your maximum. We can also have a minimum, which is represented by z equals x squared plus y squared. So again, if you plot this in your Maple calculator app, you will get something that looks like a valley or a bowl shape, with 0, 0 occurring at the very bottom of that bowl being your minimum point. And then we have the saddle, which can be shown by plotting z is equal to x squared minus y squared. So what we've done here is make the x squared and y squared terms have alternate signs. And this, as the name suggests, looks like a horse's saddle, or if you're like me and you enjoy Pringles, it kind of looks like a Pringle. So now we know what the critical points look like, we can start to answer the question about how to classify them. And in order to do this, we are once again going to take some inspiration from the function of one variable case. So to start with, let's consider a local maximum. So for a function of one variable, this is x and f of x, and a local maximum looks something like this. Now, the maximum occurs on the very peak of our hill or our mountain, and the reason this is a local maximum is that this point on the top, let's call it x0, the value of the function at x0, f of x0, is actually greater than any other value of the function f, so it's actually greater than f of x, provided x is close to x0. So we can say that f of x0 is greater than f of x for all inverted commas nearby points x. Now a local minimum works very much in the same way, except at the local minimum, which of course would have this shape, and let's suppose this is at x1, then for our local minimum, the value of f at that point must be smaller than all surrounding nearby points. So at our minimum, f of x1 is less than f of x for all nearby points x once again. So what this means overall is that at a maximum, our function f is always decreasing away from our local maximum. So a max corresponds to the function decreasing away from the maximum. And similarly, the minimum corresponds to the function increasing away from the minimum. Therefore, to check whether we have a maximum or a minimum critical point. We just in fact need to check, is our function decreasing away from the critical point, or is our function increasing? And this is where the second derivative comes into play. Now the second derivative, f double dashed or double prime of x, this is the rate of change of the derivative, or the rate of change of your gradient with respect to x. Now, the way the second derivative relates to our maximum and our minimum is to do with the fact that at the critical point, we know already that the gradient is 0. So the condition to be a critical point, and therefore to be a max or a min, was you had to be a turning point of your graph, which means your gradient passes through 0 at the critical point. And so as we move, let's say in the positive x direction, as we move to the right, the gradient begins at 0 and it's going to change. Now, there are two things that can happen here. The gradient can move to a positive value from 0 to some positive number, or it can move from 0 to some negative number. Now, if the gradient being at 0 moves to a positive number, then it is increasing. And if it is increasing, that means moving in the positive x direction, you're going on an upwards slope. So the gradient here is 0. As we move to the right, the gradient increases and moves along this positive slope. So an increasing gradient here tells us that it's a minimum. And then for our maximum, as we move to the right, our gradient goes negative and we move downhill away from this function. So our gradient is decreasing. So decreasing corresponds to a maximum. Now remember, the second derivative is the change in your gradient. So here, at a minimum, we start at 0 gradient, and then as we move to the right, our gradient increases. So our gradient, the change in our gradient is positive. It goes from 0 to a positive number. So that means our second derivative, at a minimum, is positive. So here, f dash dash of x is positive. And similarly, at the maximum, we start at gradient 0, and as we move to the right, we go to a negative value, so the value of the gradient has decreased, and therefore the decrease here corresponds to f dash dash of x being negative. So a maximum is determined by a negative second derivative, and a minimum is determined by a positive second derivative. But how does this work for our function of two variables? So we can see from our plot of the maximum that the function is actually decreasing in all directions away from our maximum critical point. So this means all of our second derivatives actually will need to be negative. So for our function of one variable, there was only one second order derivative that we can calculate, and when that was negative, we had a maximum. Now for our function of two variables, there are several second order partial derivatives that we can calculate, and at a maximum, we're actually going to need all of them to be negative because we need our function to be decreasing away in all directions, as we can see on the plot. So that means that fxx must be negative. We need fyy to be negative, and also the mixed partial fxy, which is equal to fyx for a continuous function, that must also be negative. So all three second order partial derivatives must be negative for the critical point in a function of two variables to be a maximum. Similarly, looking at the picture for a minimum, we can see that the function is increasing in all directions away from our critical point. And so at a minimum, we're going to need all of our second order partial derivatives to be positive. So fxx, fyy, and fxy, which equals fyx, assuming it's continuous, they must all be positive for a minimum. Now the saddle is a little bit trickier. We can see from our 3D plot that in some directions the function is clearly increasing, whilst in others it is clearly decreasing. So there's not necessarily going to be a universal sign or a universal rule as simple as this for the second order partials in order to determine a saddle point. And in fact, what we need to do here is to use a two-variable Taylor expansion. For a function of one variable, the Taylor expansion is as follows. So this is just the first three terms in the Taylor expansion. So f of x is f of x naught plus x minus x naught f dashed at x naught plus x minus x naught squared times f double dashed at x naught divided by 2, and we carry on in this way. As you might expect, the Taylor expansion in two variables is very similar, except now we're going to have to do partial derivatives in each of the two variables. So we have f at x and y is equal to f at x naught y naught. So this is our 0th order term, much like f of x naught, plus x minus x naught times df by dx, so fx evaluated at x naught y naught, plus y minus y naught times df by dy evaluated at x naught y naught. That will be our first order term with our first order partial derivatives, plus the second order term, which again has a very similar structure. This was going to be x minus x naught squared over 2, and then now we have fxx at x naught y naught plus y minus y naught squared f over 2 fyy at x naught y naught. And then we have the mixed term, which is plus 2 lots of x minus x naught y minus y naught all over 2 times fxy at x naught y naught plus the third order and higher terms. Now remembering that at a critical point x naught y naught, the first derivatives are 0 by definition of it being a critical point, these two terms will vanish. We can then actually take this first term across to the left-hand side and make that a minus, and then this is now equals this. So what we have is f of xy minus f of x naught y naught is now equal to these three second order terms plus higher order terms. We're actually going to neglect the higher order and say that this is in fact approximately equal to, and then we'll get rid of those higher order terms.
The next step involves various bits of algebra to simplify the equation, including dividing through by the non-zero fxx and completing the square. I'm going to skip over these steps in the video, but I've created a worksheet on Maple Learn which explains step by step how to obtain the final equation. You can follow along for yourself at the link on screen.
What we end up with is this equation, and this is going to be the key to classification of our critical points. So we have that f of xy minus f at our critical point, f of x0, y0, is approximately equal to 1 over 2 fxx, assuming fxx is non-zero, because otherwise I couldn't divide by it. Then here we've just got something which is positive, because it's a whole term here squared. So this entire bracket is always going to be positive. Then we also have something positive here with y minus y0 squared. And then we're just left with this term, fxx fyy minus fxy squared. And this is going to be our discriminant. So going back to the left-hand side of our equation and thinking about what we did in the one variable case earlier, if I'm at, let's say, a maximum, then I know that the value at my critical point x0, y0 has to be bigger than any surrounding xy point. So for a maximum, this left-hand side of my equation is going to be negative because I have a function here which is smaller. Nearby points are always smaller than the critical point that's the max. So for a maximum, the left-hand side of my equation must be negative. Now, that of course means the right-hand side must also be negative. So this term here, we've already said, is always positive because it's squared. This term over here is positive because it's a y minus y0 squared. Now, we have an fxx at the beginning, which could have either sign. But earlier, when discussing what we expect to happen at a maximum, we said that the second derivatives must be negative because the function decreases away from our maximum point. So this we actually expect to be negative. So this fxx for a maximum is negative. So now we have negative times positive, so that's negative. Then we have the discriminant and then something else that's also positive. So what that means is that in fact our discriminant must be positive. Because if our discriminant is positive, everything inside the square bracket now has a fixed sign. Everything in the square bracket is positive, multiplied by the negative fxx second derivative. That means the whole right-hand side is negative, therefore the left-hand side is also negative, and we do indeed have our maximum. So, just to reiterate, for a maximum we must have fxx being negative, and we need the discriminant fxx times fyy minus fxy squared. This must be positive. Now for the minimum, we expect the left-hand side of our equation, in the case of a minimum, this must be positive. Because for x0, y0 to be a minimal critical point, for it to be a minimum at the bottom of that bowl or valley, then all nearby points, x, y, must be bigger than the critical point. So therefore, this fxy minus the minimum must always be positive. So now we need to think, how do we ensure that the right-hand side of our equation is always positive? And it's very similar to what we see for the maximum. So again, this term is squared, so this is always positive. That will never change sign. The term on the end, y minus y naught squared, again, it's always positive. The discriminant could be positive or negative. However, we again need it to be positive, because if it's positive, everything in the square bracket has a fixed sign. It is all positive, and therefore, to make the entire equation positive, we just need f(x) to be positive. And we actually said this earlier. We said that for a minimum, we expect the second order partial derivatives to all be positive because we're increasing away from that minimal point. So for a minimum, we need f(x) to be positive, and the discriminant, again, must be positive. So you'll notice in both of these cases, the discriminant is positive. And we just determine whether we have a maximum or a minimum by the sign of f(x). It is worth pointing out that we could have, instead of factoring out f(x), I could have factored out fyy. It ever so slightly changes this. The discriminant is unchanged, and so you can either have f(x) being negative and a positive discriminant for a maximum. That could also be fyy being negative and a positive discriminant. And similarly, you could check the sign of fyy for the minimum. It doesn't matter if you check one of f(x) or fyy. If you have a positive discriminant, the sign of f(x) or fyy, either one will determine if you have a max or a min. Now finally, for the saddle point, this covers the other possible case. So we've covered the sign of the term at the very beginning outside of the square bracket. Those two cases are determining the max or the min when the discriminant is positive. So the saddle will actually happen when the discriminant is negative. So for the saddle, we just have to have, and this is the only condition that's actually required, is your discriminant must now be negative. So f(x), fyy minus fxy squared is negative. Now with the saddle, the negative discriminant means the sign of the right-hand side could be positive or could be negative. So it definitely is not a max, it's not a min, but we do know that we are at a critical point because x0 and y0 is a critical point. That's where we're doing this calculation. So if it's not a max and it's not a min, it has to be a saddle. So in summary, to classify the type of critical point for a function of two variables, you have to calculate, first of all, the discriminant, f(x), fyy minus fxy squared. You evaluate this at your critical point, x0, y0. If your discriminant is negative, you have a saddle. If the discriminant is positive, then you have to also look at the sign of either f(x) or fyy. If the sign of your second derivative is negative, you have a max. If it's positive, you have a min. So again, calculate your discriminant. Negative sign of the discriminant means saddle. If the discriminant is positive, calculate one of the other second derivatives, and the sign of that tells you if you have a max or a min. So finally, let's apply our newfound knowledge, our classification system for critical points of functions of two variables. Let's apply this to this function, f of xy is x squared plus 2xy minus y squared plus y cubed, to the critical points 0, 0 and minus 4/3, 4/3, which we found in part 1 of this video. So we already calculated df by dx, but we can quickly do that again. We're going to get 2x plus 2y for the x partial derivative. We know the y partial derivative df by dy. Again, we calculated this before as 2x minus 2y plus 3y squared. Now, our classification system using the discriminant requires us to know fxx, fyy, and fxy. So let's calculate those from these two first order derivatives. So fxx means taking another x derivative of this. So this is the only term with an x, so I'll just get 2. Fyy means taking the y derivative of this function. So that will give me, I'll get minus 2 from that term. So minus 2. And then I've got plus 6y from there. And then I also need to know fxy or fyx, which is equal for a continuous function like this. So fx and then differentiate with respect to y is going to give me just 2. So fxy is 2. And let's just do a sanity check. If I'd done df by dy and differentiated this with respect to x, I would also just get 2. So it does hold as we expect because it's a continuous function. Now, we need to calculate or evaluate these three second order derivatives at the critical point. So fxy is always 2, fxx is always 2. Now at 0, 0, what are we going to get? So at 0, 0, the discriminant, let's call it d, is going to be equal to fxx times fyy. So that's 2 times fyy, which is minus 2 when you substitute in y equals 0. So I've got 2 times minus 2, so that's minus 4. And then we subtract off f of xy squared. So f of xy is 2, squared is 4, so it's minus 4 minus 4, so that's minus 8. So the discriminant is negative. So for 0, 0, we have a negative discriminant. So our classification system says that must be a saddle. So 0, 0 is therefore a saddle point. Now, for minus 4/3 and 4/3, the discriminant d is equal to, we need to know fxx, which again is 2, multiplied by fyy. So now we have minus 2 plus 6 lots of y. So y is 4/3. So this is minus 2 plus 6 times 4/3. So 6 times 4/3, I believe, should be 8. So the 6 cancels with the 3 to give a 2, and 2 times 4 is 8. And then we also have to subtract off fxy squared. So that's again minus another 4. So overall, we've got 2 times 6 is 12, minus 4, so this one has discriminant 8. So our critical point must be a maximum or a minimum because the discriminant is positive. And then we just have to look at the sign of fxx, which is 2, which is positive, so we have a minimum. So therefore, minus 4/3, 4/3 must be a minimum. So our two critical points, in summary, we've got 0, 0 is a saddle point, and minus 4/3, 4/3 is a minimum. Thank you everyone for watching. Please do remember to subscribe to my channel if you've enjoyed this video, and hopefully I'll see you again soon.